In the last two lectures, we have discussed about basics of ionic equilibrium. In this lecture, I will discuss problems related to ionic equilibrium. The questions on ionic equilibrium are of two types. One is pH based questions and second is your solubility related problem. In this lecture, my main focus is on pH based questions. So, pH based questions. We will try to calculate pH of a solution in which concept of ionic equilibrium is utilized. So, I have already discussed with you what is pH. pH is your minus log activity of H plus ion concentration. And for dilute solution, this is simply equal to pH is equal to minus log H plus ion concentration. We have already discussed about how to calculate pH for a strong acid and strong bases. Here we do not need to apply your concept of ionic equilibrium. We do not need to apply. Concept of ionic equilibrium comes when we are dealing with weak electrolytes. What does I mean by weak electrolyte? Which dissociates a salt or a compound which dissociates not completely into water, and there is a equilibrium between undissociated and dissociated species, that is known as your weak electrolytes. Your weak bases, weak acids and salt of weak acid and weak bases comes into this category. In case of weak acids, we have equilibrium between undissociated species and dissociated species. In case of weak bases, again we have equilibrium between your dissociated and undissociated species, and similarly salt for example your Na plus plus A minus. This is irreversible, but A minus, hydrolysis of A minus giving you Ha plus OH minus. So, the equilibrium exists between these species. As a recap of last lecture, where we calculated the pH of different solutions, or for example, for weak acid we calculated H plus to be Ka into C of Ha. So, Ka is your acid dissociation constant and this is concentration of your acid, concentration of acid. For weak base, we have OH minus ion is equal to root under Kb into CbOH. Again, this is your base dissociation constant and this is your concentration of weak acid. Third, salt of weak acid and strong base. Since this is a salt of a strong base, we will start with OH minus ion concentration, and OH minus concentration will be given by Kh into sea salt. Kh is hydrolysis constant of this salt and this is the concentration of salt, and Kh in this case will be given by Kw by Ka, since this is salt of weak acid. This is salt of weak acid. So, OH minus ion concentration is equal to Kw by Ka, since Kh is equal to Kw by Ka into sea salt. If suppose I take logarithm of both sides, you will get half log Kw minus log Ka plus log sea salt. Let us take minus sign both sides, is equal to half. This will be minus log Kw, this will be minus minus plus log Ka plus minus minus log sea salt, and we know that this is equal to POH. So, POH is equal to half minus log Kw is equal to pKw and plus log Ka is equal to minus pKa plus log, this is minus. So, we keep it minus log sea salt, minus log sea salt. Again you see minus log Kw pKw plus log Ka is equal to minus pKa and you have minus log sea salt. So, minus log sea salt. So, POH will be given by half multiplied by pKw minus pKa minus log sea salt. Similarly, we can calculate pH of salt of a strong acid and weak base. For example, NH4Cl, this salt is your salt of a strong acid HCl and weak base ammonia solution. since this is a salt of a strong acid, so we will write H plus ion is equal to your Kh into sea salt, and since salt is of weak base, so Kh will be equal to Kw by Kb into sea salt. So, if I take minus log H plus ion, this will give you half log Kw with minus sign, and then minus minus plus half log Kb minus half log sea salt. So, this is pH is equal to half pKw minus half pKb minus half log sea salt, half log sea salt. This is the way we can calculate pH of salt of a strong acid and weak base. These four are very important formulas when you are trying to calculate pH, pH of a solution where concept of ionic equilibria is utilized. Now, let us see this question. What is the pH of a 0.5 molar aqueous NaCN solution, and for this pKb of Cn minus is given, which is 4.70. Now, what is given is your concentration of NaCN, and that is 0.5 molar. So, this is basically your salt concentration. Salt concentration is 0.5 molar. Now, you see NaCN is salt of a strong base which is NaOH, but weak acid which is SCN. So, in this case we can calculate OH minus ion is equal to Kh into sea salt, Now, OH minus ion is equal to Kh into sea salt. Sea salt is given, this is your 0.5 molar. We do not know the value of Kh. What is given is pKb of cyanide ion, which is 4.70. So, if we take cyanide ion plus water, what we expect that will give you SCN plus OH minus ion, and this is also the hydrolysis reaction. And since OH minus ion is given in this reaction, Kh is basically equal to Kb for cyanide ion. Now, since we know OH minus ion concentration is equal to Kh into your sea salt, we can write POH. So, let us take minus log OH minus ion concentration is equal to minus half the log KH minus half log KH minus half log sea salt, and this is POH, and this is equal to half PKH minus half log sea salt, and since pKh hydrolysis constant is simply equal to pKb of cyanide ion, which is your 4.70. So, POH will be given by half your 4.70 minus half log your 0.5, since your salt concentration is 0.5 molar. If we solve that, we can get POH, and from that you can calculate pH. So, pH is equal to 14 minus POH. pH is equal to 14 minus POH. Next question is this: the dissociation constant of a substituted benzoic acid is at 25 degrees Celsius is 1 into 10 to the power minus 4. pH of a 0.01 molar solution of its sodium salt is. Again, dissociation constant of a substituted benzoic acid is given. It means that this is salt. What we are dealing with is sodium salt of weak acid. Sodium salt of weak acid, and weak acid here is substituted benzoic acid. Dissociation constant is given, so Ka is given 1 into 10 to the power minus 4. Concentration of acid is given, C acid is equal to 0.01 molar. And what we need to find out is pH of the solution. pH of the solution. Since this is a sodium salt of a weak acid, this is a strong base. So, we will write OH minus ion concentration is equal to KH into your concentration of salt. And concentration of salt has been given. Concentration of salt is 0.01, and KH again we have Kw by K, Kw we know 1 into 10 to the power minus 14, and this is given 1 into 10 to the power minus 4 into 10 to the power minus 2. 0.01 is 10 to the power minus 2. So, you see 10 to the power minus 10 into 10 to the power minus 2, 10 to the power minus 12, and so this is 10 to the power minus 6. Under root of 10 to the power minus 12 is 10 to the power minus 6, and so OH ion concentration is 10 to the power minus 6, and then you have POH is equal to POH will be equal to 6, whereas pH will be equal to 8. It is very easy. First thing you have to decide whether salt is of a strong acid and weak base, or weak base and a strong acid. Salt can be from a strong, between a strong acid and a strong base, which we have already discussed, and salt can be between weak acid and weak base. Now, next question is this: the pOH of 0.1 molar solution of the acid HQ, weak acid, is 3. The value of ionization constant Ka of the acid is. Okay. So, pH is given for the acid and you have to tell Ka, what is the value of Ka. We know that H plus ion is equal to, for weak acid, is your Ka into C of acid, and Ka is your, you need to calculate Ka, and C acid is 0.1. Okay. What is given? pH is given, and that is your 3. So, H plus ion concentration will be 1 into 10 to the power minus 3, 1 into 10 to the power minus 3, since pH is equal to minus log H plus ion solution, H plus ion concentration. So, 1 into 10 to the power minus 3 is equal to root Ka into 0.1. So, Ka into 0.1 is equal to 1 into 10 to the power minus 6, or K will be equal to 1 into 10 to the power minus 6 divided by 0.1, and this is equal to 1 into 10 to the power minus 5 molar. Now, what we will do is, we will calculate pH of a solution when we are titrating a weak acid with a strong base. So, what we are going to discuss next is titration of a weak acid a strong base, weak acid and with a strong base. Weak acid is suppose acetic acid, and when we titrate with NOH, how pH changes. But before going to that, I will next another type of solution which is known as buffer solution. Buffer solution. These are very important solutions. They are used to maintain pH of a solution, pH of a solution. What does I mean by that? That a small addition of acid or base does not affect the pH of the solution. There are different type of buffer. First is your weak acid in presence of salt of weak acid with a strong base. So, for example, acetic acid with its salt with a strong base. Its salt with a strong base, that can be CH3COONA. So, this is weak acid, and then this is your salt of the same weak acid with a strong base. Okay. So, let us talk about this solution. So, you have a salt, and we know that since this is soluble salt, it will completely dissociate CH3COO minus plus Na plus, and concentration of this will be equal to sea salt. Since all the salt has gone to dissociated form. So, concentration of CH3COO minus will be equal to sea salt. Now, consider about this as dissociation of your weak acid. This is your CH3 CO minus plus H plus. If you start with C acid 0 0, then you can write C acid 1 minus alpha, where alpha is degree of dissociation, you will get C alpha, C alpha. Well, since we have CH3COO minus ion, so this will come into picture. So, in presence of salt, the concentration of CH3COO minus is much greater than C alpha. So, concentration of CH3COO minus ion is your C alpha plus C salt. But we know that C salt is very high in compared to C alpha, since CH3COO minus here is generated from a weak acid. So, amount of this will be always quite negligible compared to the concentration of CH3COO minus, which comes from salt. Here there is a complete dissociation, here there is a very weak dissociation. So, it is simply equal to C salt. So, if we write again CH3COOH, CH3CO minus plus H plus at equilibrium, we have C 1 minus alpha, and this is your sea salt, and this is C alpha or H plus ion concentration. This is also almost equal to C acid, since acetic acid is a very weak acid and alpha is quite smaller than 1. And so, we can simply write C 1 minus alpha is almost equal to C acid. Now, if we write Ka, acid dissociation constant, which is nothing but CH3CO minus into H plus divided by acetic acid CH3COOH, and this we already know, this is equal to C salt into H plus by this thing is equal to C acid. So, acid dissociation constant Ka is equal to C salt into H plus divided by C acid. And so, if I want to calculate H plus ion concentration, this is equal to Ka into C acid by C salt. Okay. So, pH is equal to your if I do minus log H plus minus log H plus is equal to your minus log K A minus log acid plus log salt, and this is pH is equal to pKa plus log salt by acid, salt by acid, and this is a famous Henderson-Hasselbach equation. For buffer. So, we can calculate pH by using pKa, and if we know the concentration of salt and concentration of acid. So, in the next I will discuss your titration of. So, let us go back to titration of weak acid with a strong base, weak acid with a strong base. For example, acetic acid with NaOH. And what will happen when we add NaOH from time to time? What will be the change in pH? What we are looking at is change in pH. So, let us start with 50 ml of or 0.1 molar acetic acid. Okay, and then titrate with 50 ml of 0.1 molar your NaOH. Ka for acetic acid is your around 1.8 into 10 to the power minus 5, 10 to the power minus 5 mole per liter. So, first we will start with this solution 50 ml of 0.1 molar acetic acid. So, when before the addition of NaOH, we have 50 ml of 0.1 molar acetic acid solution, and we know that pKa is equal to your minus log 1.8 into 10 to the power minus 5, which is almost equal to 4.73, So, how we can calculate pH of this? So, this is, we know that this is weak acid. So, H plus will be given by Ka into your concentration of this C acid, and so minus log H plus is equal to minus half log Ka and minus half log acid concentration, and minus log H is pH is equal to half pKa minus half log or 0.1 molar. So, we know what is the pKa value, we know the value of log 0.1. So, we can calculate pH of the solution, pH of the solution. Now, next step is what we are doing is we started adding your NaOH solution. Suppose we added 10 ml of your 0.1 molar NaOH. So, you have acetic acid plus NaOH, and what you will get is your CH3COONA plus H2O. We have initial millimole. If we just look at initial millimole of the reactant and product, we started with your this is 50 ml into 0.1 molar. So, basically 5 millimole of, we started with 5 millimole of acetic acid and we added 10 into 0.1, that is your 1 millimole of NaOH. So, what will happen is you will get 5 minus 1, that is 4 millimole, and this is 0, and how much salt is formed? 1 millimole. Okay. So, all of NaOH will react with acetic acid to give 1 millimole of, and then this. So, what in the solution you have 4 millimole of acetic acid and 1 millimole of your sodium acetate. So, again just look at it, we started with 50 ml of 0.1 molar acetic acid, or that means that we have 5 millimole of acetic acid solution. We added 10 ml of 0.1 molar NaOH, and that 10 into 0.1 is 1 millimole of NaOH. They will completely react, NaOH will go to 0. So, you are left with your, so 1 millimole of acetic acid will react with 1 millimole of NaOH to give you 1 millimole of sodium acetate, and left one is 4 millimole of acetic acid. So, now we have in the solution we have 4 millimole of acetic acid and 1 millimole of sodium acetate. So, we can apply Henderson-Hasselbach equation, which tells that pH is equal to pKa plus log salt by acid. So, pH is equal to pKa, which is 4.73 plus log. To calculate salt concentration, we will apply concentration is equal to millimole divided by volume in ml. Millimole we know, salt, the number of millimole of salt is 1 millimole. So, 1 divided by volume is 50 plus 10, 50 plus 10, 50 of acetic acid, 10 of your sodium acetate. So, it is simply 1 by 60. So, this is 1 by 60, and acid is the amount of acid is 4 millimole. So, 4 divided by your 60. So, this is 4.73 plus log 1 by 4, or simply we can write 4.73 minus log 4, minus log 4. Now, take a case when we added in the 50 ml of 0.1 molar acetic acid, we had added 25 ml of 0.1 molar NaOH. Again, we will go and do same calculation. We have CH3COH plus NaOH, neutralization reaction will happen and you will get CH3COONa plus H2O plus H2O. You had 5 millimole of acetic acid in the solution and 2.5 millimole of NaOH in solution before reaction. Suppose reaction happens, your all NaOH will go to salt, and since this is the limiting reagent and so you have 2.5 millimole of NaOH, it will interact with 2.5 ml of acetic acid to give you 2.5 millimole of sodium acetate. And here left one is 5 minus 2.5 is equal to 2.5 millimole of acetic acid. And so, again pH can be calculated using Henderson-Hasselbach equation, pKa plus log salt by acid, and pKa is 4.73 for acetic acid. So, plus log 2.5 by 2.5. Yeah, you can just divide by 75, you want concentration, but as I told you that volume does not matter here, because in numerator and denominator both will be divided by volume and they cancels out. Okay. So, what we get is 4.73 plus log 1 and log 1 is nothing but 0. So, 4.73. So, this is the way we calculate pH for a pH in the titration cases. Okay. So, first you have to know what is there in the solution, whether there is only weak acid left, whether you have weak acid plus salt of weak acid with a strong base, you have only salt. So, this is the things which first you have to understand, then only you can apply the concept of your pH calculation. So, now take another case when 50 ml of 0.1 molar acetic acid, you add 50 ml of 0.1 molar NaOH. So, equal volume is added. What will happen? Let us see here, we have acetic acid and you have added NaOH, it will give you sodium acetate and plus your sodium acetate plus your water. So, this is simple acid base reaction, acid plus base gives you salt plus water. You started with 5 millimole of acetic acid, you started with 5 millimole of NaOH and 0, 0. So, when reaction happens, all acetic acid and NaOH will go to sodium salt. So, what is left is 0 mole of this, 0 mole of this and 5 millimole of sodium acetate. So, now in a solution we have 5 millimole of CH3COONa. and total volume is equal to 100 ml. So, just we saw that we have 5 millimole of sodium acetate solution in 100 ml. Sodium acetate in 100 ml of solution. We have 5 millimole of sodium acetate in 100 ml of solution. So, concentration of salt is 5 divided by 100, 0.05 molar. Now, what will the H plus ion concentration? So, you just see this is just salt of weak acid and a strong base. So, it will be alkaline solution and you have OH minus ion is equal to KH into sea salt under root, and KH is Kw by Ka, Kw by Ka into sea salt. So, POH is equal to half pKw minus half pKa minus half log salt concentration log. So, this is your 7 minus half pK, half into 4.73 minus half log salt concentration, and salt concentration is 0.05. Just put it here, you will get POH, and from POH you can calculate pH. pH is equal to 14 minus POH. So, this is the way you can calculate your. So, now neutralization has happened. You have added 50 ml of NaOH to 50 ml of acetic acid, and almost all acid has gone to your salt. All acid has gone to salt, no base is left, no acid is left. Now, if we further add NaOH, so suppose 10 more ml of NaOH is added. So, we are dealing with a solution which has 50 ml of 0.1 molar acetic acid and 60 ml of 0.1 molar NaOH. So, if we again write a reaction CH3COOH plus NaOH giving you CH3COONA plus water. We started by 5 millimole and this is 6 millimole 0. Now, NaOH is no longer limiting agent, acetic acid becomes limiting agent, and this will totally go to salt. So, what is left out is 1 millimole of NaOH and you have a 5 millimole of sodium acetate plus water. Now, you see in the solution we have weak base, strong base, we have a strong base NaOH and NaOH, and we have salt which is CH3COONA. So, we have NaOH plus salt, and this salt is of weak acid and a strong base. But since there is NaOH and this completely dissociates, here hydrolysis is not complete, and so almost all OH minus ion will come from this base, and this is nothing but your 1 millimole. We know that 1 millimole is left, and your volume is 50 ml of acetic acid plus 60 ml of your 60 ml of base NaOH. So, 110, and once we know that what is the OH minus ion concentration, we can simply calculate minus log OH minus ion, and this is nothing but POH, and pH can be calculated from POH 14 minus POH. So, this is the way we calculate pH when we titrate a weak acid with a strong base. Similar kind of calculation can be done with when we titrate a weak base with a strong acid. When we titrate weak with a strong acid. So, let us see one more question. What is given is 0.1 molar NaOH is titrated with 0.1 molar HA till the end point. So, HA means weak acid, K is also given, K for HA is 5.6 into 10 to the power minus 6. It means that your HA is a weak acid, degree of hydrolysis is less compared to 1, very less compared to 1, then we have to calculate pH of the resulting solution at the end point. Okay. So, 0.1 molar NaOH is titrated with 0.1 molar HA till the end point. Ka for HA is 5.6 into 10 to the power minus 6, and degree of hydrolysis is less compared to 1. Okay. So, you see 0.1 molar NaOH, 0.1 molar HA till the end point. So, you have NaOH plus HA gives you Na plus H2, and so we are adding 0.1 molar, 0.1 molar, and this we know it is giving that till the end point. What does that mean? That if I start with x ml of this, I have to start with, we have to add x ml of HA, x ml of HA. So, if we take the reaction NaOH plus HA giving you Na plus water, we started with 0.x ml of 0.1 molar NaOH, and then we are titrating with x ml of 0.1. So, we will get end point when we add x ml of 0.1 molar HA. So, this will left 0, 0, and how much millimole we will get? We will get millimole as 2 into x into 0.1 millimole of x into 0.1 millimole of x into 0.1. So, if we get 0.1 into x millimole of NaOH reacts with 0.1 x millimole of HA to give you 0.1 x millimole of Na. So, in the solution we have only salt. In the solution we have only salt, which is basically salt of your weak acid and a strong base. Okay. This is millimole of Na, but what will be the concentration of Na? This will be your this millimole divided by total volume. Total volume is x plus x, 2x. So, 0.1 divided by 2 is 0.05 molar of sodium. This. Once we know the concentration of this, So, we have salt of weak acid and a strong base. Since this is salt of a strong base, we can calculate OH minus ion with this equation KH into sea salt, and KH is Kw by Ka, since this is salt of weak acid, salt, and sea salt is given. This is Kw by Ka into 0.05. So, POH will be equal to PKW half PKW minus half PKB, PKA and minus half log 0.05. This comes from your, if I take minus log OH minus ion, this will be equal to minus half log Kw plus half log Ka minus half log sea salt, and minus log Kw is equal to Pkw minus log Ka is equal to Pka, and so we have half Pkw minus half Pka and minus half log sea salt. So, by using this equation we can calculate POH, and from that we can calculate pH of the solution, pH of the solution. Now, take next question. Calculate the pH of the solution when 0.1 molar acetic acid 50 ml and 0.1 molar NaOH 50 ml are mixed, K is 10 to the minus 5. Again you see 50 ml and 50 ml same molar, and so you end up with the salt of weak acid and a strong base, and you can calculate your OH minus ion by using KH into sea salt. KH, we know that KH is equal to Kw by Ka into sea salt. So, once you calculate OH minus ion concentration, you can calculate H plus ion concentration, and then you can get the pH of the solution. So, today what we saw is how to calculate pH when two solutions are mixed, one is acid, another is base, and what we calculated is pH of a solution which results from titration of an weak acid with a strong base. Thank you.